Welcome to this Kubernetes technical interview questions and answers video. If you notice, with the rise in containerization, Kubernetes has become one of the most sought after skills for DevOps engineers. Whether you're a seasoned DevOps pro, on the verge of launching your career, or anywhere in between, understanding Kubernetes is a non-negotiable asset. So as we get started with this exclusive episode of our technical interview series, we've dedicated the spotlight entirely for Kubernetes. And yes, I know watching videos could sometimes feel like a daunting task, but here's the truth about it. If you're looking to secure a new job or craving your path back into the job market, mastering these interview questions is your golden ticket. But as we all know, DevOps engineers are handsomely compensated, often earning between $140,000 to $300,000 due to the value they provide, and Kubernetes usually constitutes a significant portion of the skills required for that role. As part of this video, we'll explore 12 scenario-based questions commonly asked during technical interviews. So sit back, relax, and let's demystify Kubernetes together. Question number 1. I saw in your resume that you've been using Kubernetes for the past 7 years. Is that correct? And if yes, I would like you to imagine a situation where you need to create a Kubernetes pod running on an Nginx container. You have a manifest at your disposal, which includes the necessary container specifications. Can you walk me through the process of applying this manifest and what you do to make sure that the pods are running as expected? If asked that question, I'll say, yes, that's correct. I've had the privilege of working with Kubernetes for the past 7 years, gaining an in-depth knowledge and practical experience in managing containerized applications at scale. Creating a pod running on an Nginx container is a common task in Kubernetes, and over the years, I've refined my approach to handle it efficiently. First, I'll navigate to the directory containing the YAML manifest, ensuring I have the necessary permissions to apply the configurations to our Kubernetes cluster. I usually check out a few things. Number 1 is the file availability. Then I check out the file permission and go through the file content and syntax as well. I always tell junior DevOps engineers how essential it is to run the kubectl plan command before ever applying that manifest. This command checks the validity of the manifest file without actually creating any resources. It helps you identify any syntax errors, missing fields, and gives you an overview of what is going to be applied. And if everything looks good, I'll go ahead to run the kubectl apply command to create the pod based on the manifest. So in this scenario, I'll run kubectl apply-f nginxpod.yaml. This command tells Kubernetes to apply the configurations defined in the nginxpod.yaml manifest file. To be sincere, this question relates a lot to what I do at my current position. At my current position, we frequently use Kubernetes to deploy microservices. In my recent project, we needed to launch a new service, and I followed a similar procedure to create a pod with specific container specifications. And once the pod is created, I use the kubectl getPods command to check the status of all pods running in the cluster, specifically focusing on the Nginx pod to ensure that it's in the desired state needed. This meticulous approach ensures the successful deployment of the Nginx container, and most importantly, it guarantees that our application is serving traffic as intended. While this process sounds straightforward, doing this for about 7 years has taught me to pay attention to details in each step of the process. It's not just about creating pods, but it's also important to make sure that the pods run seamlessly, which is very important in maintaining the reliability of our services. Question number 2. Picture a scenario where you had several pods that need to communicate with one another using DNS. Could you walk me through how Kubernetes handles DNS resolutions, enabling pods to discover and communicate with other pods? Additionally, could you provide me an example illustrating 2 pods effectively communicating through DNS within the Kubernetes cluster? Absolutely. Service discovery within Kubernetes is like having a dynamic phone book for your pods, making communication a breeze. Let me break it down for you. In the Kubernetes manifest, you typically define a service resource alongside your pod configurations. The service acts as a stable endpoint that abstracts the underlying pods, making it easier for other pods to discover and communicate with them. Here's how it works. When you create a service, it's associated with a set of pods based on the defined label selectors. These pods become part of the service, and the service assigns a DNS name to itself. For example, if you create a service named MyService, it automatically gets a DNS name like myservice.namespace.svc.cluster.local. Now, when one pod wants to reach another, it can simply use the DNS name and Kubernetes takes care of the rest. Kubernetes DNS service resolves the DNS name to the IP address of one of the ports behind the service. This way, ports can dynamically discover and communicate with one another using the DNS name associated with the service. For instance, if port A wants to reach my service, it uses the DNS name and Kubernetes ensures that the traffic is routed to one of the ports that is part of my service. This mechanism makes service discovery incredibly flexible and dynamic, as ports can come and go, but the service and the DNS name remains consistent. So in summary, service discovery in Kubernetes is made possible by defining the services in your manifest, which provides the DNS names for the ports, and Kubernetes built-in DNS service takes care of resolving those names to the correct port IDs. This powerful combination simplifies communication and enables dynamic scalability within the Kubernetes cluster. Question number 3. Could you share your experience with the types of Kubernetes clusters you've worked with in the past? Have you ever had the opportunity to construct a Kubernetes cluster from ground up, managing all of its aspects independently? If asked that question, I'll say, thank you for asking that question. I've had the privilege of working both with the self-managed Kubernetes cluster as well as Amazon EKS, each offering unique advantages and challenges. In the self-managed cluster setup, I had complete control over the cluster's infrastructure and components. I constructed it from scratch, starting with the master node, which had the Kubernetes control plane components like the API service, etcd, and scheduler. This control plane was responsible for managing and orchestrating the cluster's worker nodes. Speaking of worker nodes, we had a significant number of them, each running Kubernetes components like kubelets, kubeproxies, and the container runtime. Our application workloads were distributed across the worker nodes, and we had to manage their scaling, monitoring, and maintenance manually. One of the challenges we faced was ensuring volume persistency, particularly for the stateful workloads. We implemented solutions like persistent volumes and persistent volume claims to manage data storage across our pod efficiently. While this gave us granular control, it was also time-consuming to set up and maintain. Updates and upgrades to the Kubernetes version was another area where self-management required significant effort. We had to carefully plan and execute updates, considering potential downtimes and compatibility issues. Scaling the cluster to accommodate growing workloads and orchestrating rolling updates for certain deployments were tasks that demanded careful coordination as well. To monitor our self-managed clusters, we deployed Prometheus agents using stateful sets to ensure reliable monitoring and alerting. Additionally, we had 2 separate clusters for high availability and disaster recovery. If one cluster experienced issues or failures, our application could continue running without disruption, thanks to its load balancers and failover mechanisms. Now, let's talk about transitioning to Amazon EKS. Moving to EKS provided a significant shift in our cluster management approach. Amazon took over the responsibility of managing the Kubernetes master nodes, allowing us to focus more on our application workloads. This shift significantly reduced the operational overhead related with maintaining the control plane. Updating and upgrading Kubernetes became more streamlined with EKS as AWS handled the control plane updates seamlessly. This automation not only simplified the process, but also ensured that we were running on the latest, most secure Kubernetes versions. In summary, while the self-managed Kubernetes cluster provided more insights and control, transitioning to Amazon EKS offered operational ease and scalability. The move allowed our team to focus more on our application development and less on the infrastructure management, ultimately improving our efficiency and enabling us to deliver more robust and scalable services to our users. Question number 4. Let's say you're dealing with an application that sometimes experiences high traffic during specific hours of the day. How can you handle scaling it? Oh, that's a nice one. I would love to use this opportunity to share how we handled scaling for a critical banking application of one of our fintech clients. For this project, we had recognized the importance of ensuring that the application could seamlessly handle sudden surges in traffic, especially during peak banking hours. Kubernetes played a pivotal role in achieving this. We started by configuring Kubernetes horizontal pod auto-scaling. This is a Kubernetes feature that automates the scaling of pods within a deployment or replica set based on certain metrics or criteria. It allows Kubernetes to dynamically adjust the number of running pod replicas to match the current workload, ensuring optimal resource optimization and application performance. So to begin, we had to define the appropriate metrics that would trigger scaling decisions. For this banking application, CPU utilization was a crucial metric. as it indicated the amount of workload on application servers. We also monitored custom application-specific metrics like the number of active user sessions and transaction processing rates. Once our metrics were in place, we created a horizontal pod autoscaler resource within our Kubernetes manifest file. These resources allowed us to specify the target metrics such as CPU utilization and set the desired resource utilization level as well. For instance, for this specific project, we had the threshold at 70% for CPU utilization. With this setup, Kubernetes constantly monitored the application's performance. When the CPU utilization went above 70%, Kubernetes automatically created additional pod replicas for our banking application to handle the increasing load. Scaling wasn't only done at the pod level. Additionally, we applied cluster autoscaling to ensure that our underlying infrastructure could also expand as needed. For instance, if the Kubernetes nodes had reached a capacity, cluster autoscaling will automatically provision additional worker nodes accommodating the newly created pod replicas. This approach not only ensured our banking application's availability and responsiveness during peak times, but also optimized resource utilization during quiet periods, helping us contain and optimize cost. In summary, Kubernetes horizontal pod autoscaling, backed by a well-defined metrics and resource utilization threshold as well, allowed us to make our fintech client's banking application highly responsive to fluctuating user demand. Question number 5. How do you limit CPU and memory usage for pods in your current role? If asked that question, I'll say, in my current role, managing CPU and memory limits for pods is a critical aspect of ensuring optimal resource utilization and application stability. Kubernetes provides us with the flexibility to define these limits efficiently. To set CPU limits, I typically include it in the resource section within the pod manifest file. Here, I specify the CPU limit using the limits field, such as CPU 0.5, to limit a pod to half of the CPU core. This ensures that the pod doesn't consume more CPU resources than allocated, preventing resource contention and performance degradation. For memory limits, I follow a similar approach within the resource section of the manifest file. I use the memory field to specify the memory limits in megabytes, for example, 256 MI. By defining these limits, Kubernetes ensures that the pod operates within the allocated resource boundaries. If a pod attempts to exceed its limit, Kubernetes takes the appropriate action, such as throttling CPU usage or terminating the pod to free up resources. This proactive resource management enhances application stability, prevents resource contention, and optimizes the overall cluster performance. Moreover, I regularly monitor the pod resources using Kubernetes built-in metrics and observability tool called Prometheus and Grafana. This enables me to fine-tune resource limits based on real-time data, ensuring that our application is consistently performing at its best while efficiently utilizing cluster resources. Overall, setting and managing CPU and memory limits for pods is an essential practice in my role. It helps guarantee the reliability and efficiency of our Kubernetes-based applications. Question number 6. In this role, security and configuration management plays a crucial part in ensuring the reliability and safety of our applications. Can you please explain how config maps and secrets are used in Kubernetes for managing application configuration and sensitive data? And also share any real-world scenario where you've had the chance to apply these concepts efficiently. If asked that question, I'll say, config maps and secrets are fundamental Kubernetes resources that help in managing application configuration and sensitive data respectively. Security is paramount in my organization, and this doesn't only apply for Kubernetes. Config maps are used to store configuration data that can be consumed by containers within pods. They are often employed to separate configuration details from application codes, allowing for more flexible and easier updates. Config maps are typically used for non-sensitive data like environment variables, configuration files, or command line agreements. Secrets, on the other hand, are specifically designed for managing sensitive information such as API keys, passwords, or tokens. Kubernetes uses base64 to encode secret data, ensuring it remains secure. Secrets provide a way to securely pass sensitive information to pods without exposing it directly in the pod configuration. This is crucial for maintaining the security of the application and adhering to best practices. Question number 7. Imagine you're managing a stateful application that relies on stable network identifiers. In Kubernetes, stateful applications often have a unique requirement compared to stateless ones. Can you describe the challenges you might face in deploying and maintaining such an application? And how would you address the challenges to ensure a stable network identifier within the Kubernetes cluster? If asked that question, I'll say, managing stateful applications in Kubernetes requires careful consideration of network identifiers and other factors. Here are some key challenges and strategies I currently use to ensure stable network identifiers. Number 1. Port identity. Stateful applications typically rely on stable network identifiers like hostnames to communicate between ports. To achieve this, Kubernetes offers a feature called stateful sets, which assigns predictable port names and persistent network identifiers based on an ordinal index, for example, port 0, port 1. This ensures that the port maintains consistent identifiers even during rescheduling or scaling events. Number 2. Storage and data persistency. Stateful applications often require persistent storage for data durability. Kubernetes provides persistent volumes and persistent volume claims to manage data storage. Ensuring that the persistent volume claims are correctly bound to the appropriate persistent volume is crucial for maintaining data integrity and availability. Number 3. Headless services. In Kubernetes, headless services can be used to enable direct connection with the individual ports within a stateful set, allowing the clients to discover and connect to the port using DNS names that correspond to their stable network identifiers. Number 4. Scaling and updates. When scaling stateful sets or performance updates, it's important to ensure that new ports are created with consistent network identifiers. Properly managing rolling updates and port termination ensures that the network stability is maintained. Number 5. Monitoring and observability. Implementing monitoring and observability tools such as Prometheus and Grafana can help detect and troubleshoot issues related to network stability in stateful applications. These tools provide insights into the port communication and resource usage. Number 6. Backup and recovery. Having robust backup and recovery mechanisms in place is essential for data-intensive stateful applications. Regular backup of data and configuration helps to ensure resilience and facilitates disaster recovery. In summary, managing stateful applications in Kubernetes involves addressing challenges related to stable network identifiers, persistent storage, scaling, updates, monitoring, and data management. Leveraging Kubernetes features like stateful sets and headless services, along with best practices, can help ensure the stability and reliability of stateful applications within a Kubernetes cluster. Question number 8. I noticed you said something about persistent volume earlier on. If you need persistent storage for an application, how can you achieve that, or how can you set it up? If asked that question, I'll say, certainly. In one of my previous roles, we had a critical banking application hosted on Kubernetes, and we needed to ensure robust and scalable persistent storage. To achieve this, we integrated Kubernetes with some AWS services. We began by defining an AWS Elastic Block Store storage class in Kubernetes. This storage class leveraged AWS EBS volumes, which provided a reliable and scalable block storage. AWS EBS allowed us to dynamically provision volumes that attached the performance characteristics required by our application, whether it was a high-speed SSD or a cost-effective HDDS. Next, we created persistent volume claims in our application deployment manifest. These persistent volume claims were configured to request storage from the AWS EBS base storage class. Kubernetes, in conjunction with AWS, automatically provisioned EBS volumes as persistent volume claims were created, ensuring that we had the right amount of storage for our applications. In our scenario, the application needed to handle a surge of traffic during peak banking hours, which required scaling both compute and storage resources. We implemented Kubernetes horizontal port autoscaling to dynamically adjust the number of application ports based on our CPU utilization metrics. Simultaneously, AWS autoscaling groups were configured to scale and underline EC2 instances based on demand. The integration with AWS also extended to data backup and disaster recovery. We use AWS Backup to create automated backups of our EBS volumes, ensuring data integrity and providing the ability to restore data in case of any issues. Moreover, we utilized AWS Identity and Access Management for secure access to our AWS resources, ensuring that only the authorized entities could manage and interact with our persistent storage. This integrated approach allowed us to seamlessly scale our application during traffic spikes, ensuring data durability through automated backup and provide robust security through AWS IAM. It was a successful implementation that combined Kubernetes dynamic orchestration capabilities with AWS reliable and scalable storage services. In this scenario, integrating Kubernetes with AWS services like EBS, HPA, autoscaling, AWS backups, and IAM also allowed us to create a highly available and resilient banking application with scalable and secure persistent storage. Question number 9. Let's say you had multiple services running in your Kubernetes cluster and you wanted to expose some of them to the internet. How would you do that? If asked that question, I would say, to expose multiple services to the internet efficiently in Kubernetes, I'll typically follow the following steps. First, I'll identify the service that needs to be exposed. In Kubernetes, this is typically done by creating Kubernetes services of type load balancer or node port. Load balancer is the preferred choice if you're running your cluster in a cloud environment like AWS, Azure, or GCP, as it automatically provisions external load balancers. Next, I'll create a Kubernetes service object for each of the services that needs to be exposed. This service object acts as an entry point for incoming traffic. In each service definition, I will specify the target port or entry point that the service should route traffic to. For a scenario where I'm working with a cloud provider like AWS, I'll use a load balancer service type. This service type interacts with the cloud provider's load balancer service, which for AWS is ELB, to distribute the incoming traffic across ports or services. After creating the services, Kubernetes takes care of the heavy lifting. It automatically interacts with the cloud provider's infrastructure to provision an external load balancer or allocate a node port depending on the service type chosen. Once the services are configured, I'll verify the setup by checking the status of the services using kubectl get services or by inspecting the cloud provider's load balancer's configuration. In summary, exposing multiple services to the internet in Kubernetes involves creating service objects of type load balancer or node port. Kubernetes, in coordination with the cloud provider, handles the creation of the external load balancers, making the services accessible from the internet. This approach allows for a seamless and scalable way to expose services while maintaining high availability and reliability. Question number 10. Imagine you want to control the placement of pods in your cluster. How would you achieve this? And what Kubernetes features or resources could you use? If asked that question, I will say, to control the placement of pods in my Kubernetes cluster, I'll utilize Kubernetes features like node affinity, node tainting, and toleration. Node affinity allows me to specify rules that influences which nodes in the cluster a pod can be scheduled on. For instance, if I have pods that require specific hardware resources or needs to run nodes with specific labels, I would define node affinity rules to express these requirements. This way, Kubernetes will schedule pods only on nodes that matches the defined credentials. Node taints are used to mark nodes as unsuitable for certain pods unless those pods have specific tolerations. This helps control which pod can run on particular nodes. For instance, I could taint nodes to prevent general purpose pods from running on them, and then use toleration to allow specific pods that require those nodes' specialized resources. By effectively using these features, I can fine-tune the placement of pods in the cluster, ensuring they land on nodes that meet their requirements and constraints. This level of control is valuable for optimizing resource utilization, achieving better performance, and managing workload with specific needs. Question number 11. Imagine you're working with a custom application that has specific resource requirements. How would you define and allocate these custom resources within the Kubernetes cluster, and what Kubernetes resources or configurations would you use? Working with custom applications that have specific resource requirements in Kubernetes involves careful planning and configurations. First, I'll thoroughly analyze the application's need to determine its CPU and memory requirements. This analysis may include profiling the application under typical workloads to understand its resource consumption patterns. Once I have a clear understanding of the resource needs, I'll update the Kubernetes manifest for a custom application. In the manifest file, I'll specify these resource requirements using resource sections under the container specification. This is where I will define both requests and limits. For example, if the application needs a minimum of 4 CPU cores and 8 GB of memory to operate efficiently, I'll set the request to ensure it gets at least that amount. Additionally, I'll set limits to establish an upper boundary, preventing the application from consuming excessive resources and causing resource contention with other pods on the same node. After configuring the manifest with the resource requirements, I'll apply it to the Kubernetes cluster using kubectl apply command. This will deploy the custom application with the specified resource setting. Once the application is running, the job doesn't end there. Continuous monitoring becomes crucial. I'll use Kubernetes monitoring tools like Prometheus and Grafana to keep a close eye on resource utilization. This real-time visibility helps ensure that the allocated resource aligns with the application's demand. If I notice any deviations or bottlenecks, I'll make the necessary adjustment to the resource settings. In summary, managing custom resource requirements in Kubernetes involves a holistic approach, from initial analysis to fine-tuning through monitoring. This ensures that the application receives the necessary resources for optimal performance while maintaining resource efficiency across the cluster. Question number 12. Let's say you're overseeing a Kubernetes cluster and one of the pods isn't behaving as expected. How would you approach troubleshooting this issue? If asked that question, I'll say, certainly. When it comes to troubleshooting Kubernetes issues, I relied on a structured methodology to effectively identify and resolve problems. Here's the step-by-step methodology that I follow. I start by gathering information. The initial step involves collecting pertinent information about the issue. I'll check the Kubernetes event logs, pod logs, and the application logs to get insights into what might be causing the issue. This initial information helps me to pinpoint the root cause of this issue. Once that's done, I'll examine the resource utilization. Resource utilization, such as CPU usage or memory usage, can play a significant role in unexpected pod behaviors. I'll analyze the resource consumption of that affected pod to ensure that it's not exceeding its limit or facing resource contention issues. I'll then move on to checking network connectivity. Networking issues are common culprits in misbehaving pods. I'll identify the network connectivity of the pod, making sure it can reach the required services and that there are no networking policies or firewall restrictions causing problems. Once that's done, I'll go ahead to inspect the configuration. Configuration issues can lead to unexpected behavior. I'll carefully review the Kubernetes manifest file for the pod and ensure that the configurations align with the intended state of the application. If the application relies on any external services or dependencies, I'll investigate the status of those dependencies. Ensuring that the external services are functioning correctly is crucial, as issues with dependencies could sometimes have cascading effects on the application's behavior. And finally, I'll check every monitoring tool as well as the log and metrics attached to that application. In summary, effective Kubernetes troubleshooting hinges on a systematic approach that encompasses log analysis, resource assessment, network validation, and configuration verification. This approach ensures that issues are swiftly identified and addressed, preventing the stability and reliability of Kubernetes-based applications. And there you have it, 12 scenario-based Kubernetes questions that will prepare you for any Kubernetes technical interview. Remember, Kubernetes is not just a skill, it's a valuable asset that will enable you to navigate a dynamic landscape of modern software development and infrastructure management. As you continue your journey in DevOps, these insights and knowledge will serve as a solid foundation, helping you to excel in interviews and contribute effectively to your organization's success. Thank you for joining us, and until next time, stay grinding. Cheers.